This lesson is entitled Limits Involving Infinity, Asymptotes of Graphs. In this lesson, we investigate the behavior of a function when x becomes increasingly large, when x approaches either infinity or negative infinity. How is the function behaving? Also, we study something called infinite limits, and that's when the function values are uh, becoming arbitrarily large in magnitude. So to get us started, I would like for us to consider the function f of x is equal to 1 over x. The function 1 over x has the following graph. We do know that x cannot be 0, so there is a vertical asymptote here on the y-axis. So the function's undefined when x is equal to 0. And so what I would like for us to consider is the limit of our function as x approaches positive infinity. That is to say, as x values get arbitrarily large. So as you allow x to approach infinity, notice that your function values are decreasing and they're getting closer and closer and closer to the x-axis, which means your function values are approaching a real number, namely 0. Also, notice that the limit of our function as x values approach negative infinity. So now I'm over here as x values get, tend toward negative infinity. Your function values are approaching the x-axis and getting infinitely close to 0. Now, the main thing I really would love for you to take away from this is the limit as x approaches infinity and negative infinity is equal to a real number. In this case, it's equal to 0. So because we're allowing x to approach infinity and negative infinity, we are calling these limits at infinity. Limits at infinity. Okay, let's calculate the following limits. So I've given you one so far. After we look at this one, I'll show you another limit. Here we're considering the limit as x approaches infinity of 5 plus 1 over x. Now we can use our sum rule to say this is equivalent to the limit of the sum is equivalent to the sum of the limits. So the limit as x approaches infinity of 5, the first addend, plus the limit as x approaches infinity of 1 over x. Now, the limit of a constant like 5 is just 5, right? Plus, and then we just talked about how the limit of 1 over x as x approaches infinity is 0. So this is 0. So then the limit here is 5. Check this out. The limit as x approaches negative infinity of pi root 3 all divided by x squared. All right, so let's see if we can start breaking this down. This is equivalent to the limit as x approaches a negative infinity of, let's see, we can rewrite this expression as, what would be nice? Pi times root 3, right? Times 1 over x squared. Let's write it like this, 1 over x times 1 over x, like that. Now, we can use the product rule here to say the limit of this product is equivalent to the product of the limits. So we can say this is equivalent to the limit as x approaches negative infinity of this constant pi root 3 times the limit as x approaches negative infinity of 1 over x times the limit as x approaches negative infinity of 1 over x. Now, again, this is a constant. Pi root 3 is a constant, so that's just pi root 3 timed, and then again, we just determined that the limit of 1 over x as x approaches negative infinity is 0, so then this is going to be times 0 times 0, so this limit is 0. These are limits at infinity. Now let's talk about limits at infinity for rational functions. Now we're going to use a strategy here. It's a popular strategy, and that is whenever we have a rational function, we are going to divide the numerator and the denominator by the highest power of the variable that appears in the denominator. Then the result will depend on the degrees of the polynomials involved. For example, here we have the limit as x approaches infinity of this rational function, 5x squared plus 8x minus 3, all over 3x squared plus 2. Now, the largest power of x in the denominator is x squared. So what we're going to do is divide every term in the numerator and every term in the denominator by the same thing, and that is x squared. All right. So then when you divide every single term by x squared, this first term, 5x squared divided by x squared, is just 5. 8x divided by x squared would be 8 over x. All right. And then finally, negative 3 divided by x squared is just negative 3 over x squared. Now, we're going to do the same action in the denominator, and you'll end up with 3 plus 2 over x squared. We know this is valid because when you divide the numerator and the denominator by the same thing, that being x squared in this case, you're really multiplying the entire expression by 1, the entire function by 1. So whenever you multiply any expression by 1, the value of that expression does not change. So this here is an equivalent expression. Now, consider the limit as x approaches infinity. This term here is going to 0 because the denominator is growing larger and larger while the numerator remains fixed at 8. The same is true about 3 over x squared and 2 over x squared. All of those terms are approaching 0, while 5 is constant and 3 is constant or fixed. So then you have 5 plus 0 over 3 plus 0. That is to say, the limit is 5/3. Notice what's interesting is that the limit is basically the ratio of your leading coefficients in the very beginning. The leading coefficient of the numerator was 5. The leading coefficient of the denominator was 3. And 5 over 3 happens to be the limit we were looking for. Let's look at another rational function. Now we are considering the limit as x approaches negative infinity of 11x plus 2 all over 2x cubed minus 1. Now, if we apply our strategy, then that means we're going to divide the numerator and the denominator by x cubed, because x cubed is the largest power of the variable that's in the denominator. So then this is equivalent to the limit as x approaches negative infinity of, all right, folks, let's divide every single term in the numerator and the denominator by x cubed. The first term in the numerator becomes 11 over x squared. And then the second term in the numerator becomes 2 over x cubed. And in the denominator, you have 2 minus 1 over x cubed. Now, as x values tend to negative infinity, this denominator here grows without bound, and the numerator remains fixed at 11. That means this entire ratio is approaching 0. The same can be said about this ratio, and the same can be said about this ratio. So this limit is 0 plus 0 in the numerator over 2 minus 0 in the denominator. All of this leads to a limit of 0. Notice that this limit at infinity, this is a limit at infinity here, is a real number, which is 0. Okay, so what is very important is that you identify or observe that the limits at infinity that we've been finding have been real numbers. If the limit at infinity, the limit as x goes to infinity, or the limit as x goes to negative infinity happens to be some number b, that means the graph has a horizontal asymptote, namely y equal to b. That's really important. If your limit at infinity is a real number, some real number b, in the previous case the limit was 0, so that for that function your horizontal asymptote will be y equal to 0, right? So whatever, if you get a real number for your limit at infinity, if you get a real number, that means that real number is a horizontal asymptote for the graph of your function. Y equal to b is a horizontal asymptote for your function. Now, the graph of your function can have, it can have no horizontal asymptotes. It can have one horizontal asymptote, two horizontal asymptotes. It depends on whether the function has these limits at infinity. So let's look at the following example. I think the next example I'm about to show you, you're going to see that the graph of this function has two horizontal asymptotes. Let's check it out. All right, we are being asked to find the horizontal asymptote or horizontal asymptotes, right? There could be more than one, of the graph of this function. Now, in order to find the horizontal asymptote or horizontal asymptotes of the function, we need to consider a limit at infinity. So let's do that now. Let's consider the limit as x approaches positive infinity, and let's consider the limit as x approaches negative infinity. Okay, first, for positive values for x, we are calculating the limit as x approaches positive infinity, right? That positive values for x means x is approaching positive infinity for our function. Now, if x is positive, then this limit is equivalent to the limit as x approaches infinity of x cubed minus 2 over x cubed plus 1. You do not need the absolute values bars here because we already know x is positive. So the absolute value of a positive number is positive. And so the absolute value bars are redundant in this case. Now, this is a rational function. This is the strategy, folks. This is the idea. They're asking us to find the horizontal asymptotes for the graph of this function. If you can show that the limit at infinity is a real number, some real number, then you have not only shown that there's a horizontal asymptote, you have actually found where it is. Okay, so the whole idea is to show that this rational function has a limit at infinity that's a real number. Okay, let's use our strategy. Our strategy is to divide the numerator and denominator by the highest power of the variable in the denominator. That being said, the highest power that you see in the denominator is x cubed. We're going to divide every single term by x cubed. So this becomes the limit as x approaches infinity of, now I want you to take each term in the numerator and in the denominator and divide them by x cubed. You end up with 1 minus 2 over x cubed, and then all of that over 1 plus 1 over x cubed. Now remember, you're letting x approach infinity. That means this ratio here is going to 0. Likewise, this ratio is going to 0. So then you're left with 1 minus 0 over 1 plus 0. So the limit, look at this, is a real number. So this right here, the fact that the limit at infinity is a real number shows that this graph has a horizontal asymptote. What is it? Y equal to 1. All right, very good. What we want to do next is consider x values that are less than 0. In other words, the limit as x goes to negative infinity. Let's do that. All right, for this case, for x values that are less than 0, we are calculating the limit as x approaches negative infinity of our function. Now, if x is less than 0, that means x is negative. That means the absolute value of x is going to be equal to the opposite of x. All right, so let me change this. This is equivalent to the limit as x approaches negative infinity of x cubed minus 2. And if you want to get rid of the absolute value bars here, the absolute value of x, remember x in this case is negative, the absolute value of a negative value is something positive. So then this can be rewritten as negative x cubed. Remember, and then plus 1, of course. Remember that x is negative. So negative of a negative is a positive. So this is definitely positive, as is the absolute value of x. So these are equivalent expressions. All right, so very good. Now, what are we doing? We are considering the limit as x goes to negative infinity. And so let's use our strategy once again. We are going to divide every single term in the numerator and the denominator by the largest power of the variable in the denominator, which again is x cubed. So divide every term by x cubed. You get 1 minus 2 over x cubed over negative 1 plus 1 over x cubed. Now, keep in mind that we want to show, hopefully, that this is a real number. So you end up getting 1 minus 0 over negative 1 plus 0. And all of this is equal to negative 1. And the big idea here is you have a real number. Because negative 1 is a real number, you found a second horizontal asymptote for your graph. So we see this function has 2 horizontal asymptotes. That's really, really, really interesting. All right, cool. Let's move on. All right, now we're being asked to find the limit of sine of 1 over x as x approaches positive infinity. Now, we already know about this ratio, 1 over x. If the numerator is fixed at 1 and the denominator is growing without bound, then this ratio, 1 over x, is approaching 0. So we know 1 over x is approaching 0 as x values tend to positive infinity. Therefore, this limit is equal to 0. Because sine of a really small value, we know how the sine function behaves near 0. Your function values are approaching 0. Check this one out. This one's really interesting. It's the limit of x minus the square root of x squared plus 16 as x approaches infinity. Now, as x tends to infinity, this first term is approaching infinity, and so is this term. So, this is really weird because this ends up being infinity minus infinity, which doesn't really make sense. So, you and I are going to have to be clever on how we choose to rewrite this expression so we can actually figure out what the limit is, okay? Now, remember, in the graphical representation is if you and I can find that the limit at infinity is equal to a real number, then we have found a horizontal asymptote for the graph of our function. Okay, so one strategy that is very popular is to multiply the numerator and the denominator of this expression by the conjugate radical expression. Remember, the conjugate radical expression is just the opposite operation. So the conjugate radical expression for this radical expression will be x plus the square root of x squared plus 16. Now we know this is valid because this is equivalent to multiplying by 1, which doesn't change the value of our expression. So then this becomes, let's see, the limit as x approaches infinity. This numerator, if you multiply, gives you x squared minus x squared plus 16 all over x plus the square root of x squared plus 16. Now continuing to simplify, let me move up here. This now leaves us with the limit as x approaches infinity. Look at this numerator. All you're left with is negative 16 over this denominator. Now, remember that your x values are growing without bound, right? So your denominator, therefore, is approaching infinity. It's getting bigger and bigger and bigger, while your numerator is fixed. Your numerator remains constant. That means the limit is going to be 0, which is a real number. So if you were to consider the graph of our function, you have just found y equal to 0 to be a horizontal asymptote. Hey folks, here I could have also divided every term in the numerator and denominator by the largest power of the variable in the denominator, which is x, not x squared, because the square root of x squared is x. So the largest power is x. If I would have divided every single term by x, then I would have gotten 0 as well. So that's just another way I could have done it. All right, beautiful. Good job. All right, now let's look at this example. But before we do, I just want you to really observe something. The functions we have seen before this one, the degree of the numerator has always been less than or equal to the degree of the denominator. Once again, all of the functions that we've looked at so far, the degree of the numerator has been less than or equal to the degree of the denominator. And every single time, the limit as x goes to positive or negative infinity turned out to be a real number, which produced a horizontal asymptote of the graph. In this example, the degree of the numerator is not less than or equal to the degree of the denominator. In fact, the degree of the numerator is actually greater than the degree of the denominator. We're going to see that this will not produce a horizontal asymptote. Instead, it's going to produce an oblique or slant asymptote for the graph. The first thing I want us to consider is rewriting our function. So our function is x squared minus 3 over 2x minus 4. And the reason why I'm having us think about rewriting it is because we're going to find or calculate the limit as x goes to positive and negative infinity. And as of right now, the numerator, as x gets closer and closer to negative or positive infinity, the numerator is going to infinity, and so is the denominator. So let's consider rewriting this. And the way I'm going to rewrite it is by actually performing this operation of division. So the numerator is always my dividend, and my denominator is always my divisor. All right, notice that I inserted 0x for the missing first degree term. And so when you do this division here, I know 2x times something will give me x squared, and that something is x over 2, or 1/2 x, right? 2x times x over 2 will be x squared, and then negative 4 times x over 2 will be negative 2x. I will subtract all of this, and that leaves me with a positive 2x. I'll bring down this minus 3. And I repeat the cycle. 2x times 1 will give me what I need. 2x times 1 is 2x. And negative 4 times 1 is negative 4. Again, we're subtracting. So then this turns out to be 1. So what we just determined is that our function can be rewritten as the quotient plus the remainder over the divisor. This is an equivalent expression for our function. Now, please keep in mind this part is the quotient and this part is the remainder. okay? Notice that your quotient is linear. This is a line. This defines a line. All right. So what we see is that as x values grow arbitrarily large, as x approaches infinity and negative infinity, the end behavior of the function approaches a line. It approaches this quotient. Because keep in mind, as x values grow really large, folks, this numerator's fixed at 1 and the denominator's growing, right? And so this remainder is approaching 0, so it's becoming insignificant. And the end behavior of the function is approaching this linear expression or this line. So then our end behavior asymptote is not horizontal, it is oblique or a slant asymptote. And it has the equation y equal to x over 2 or 1/2 x plus 1. So this is your oblique or slant asymptote. So please notice that when the degree of the numerator, going back to what I said earlier, when the degree of the numerator was less than or equal to the degree of the denominator, we got a horizontal asymptote for our graph. And when the degree of the numerator is 1 more than the degree of the denominator, that's the case where we got an oblique asymptote. We now shift our attention to infinite limits. So I want us to reconsider this function f of x is equal to 1 over x. And I want us to consider what the limit of this function is as x approaches 0, let's say from the right. So the limit as x values approach 0, let's for now just consider as x values approach 0 from the right. Notice that the function values grow arbitrarily large, right? Grow without bound. They tend toward positive infinity. There is no real number. There is no positive real number that your function values reach. I mean, it just keeps getting larger. They just keep getting larger and larger and larger. And so, although we say it has no limit, f has no limit as x values approach 0 from the right, because infinity is not a real number, it is still helpful to write that the limit as x approaches 0 from the right is positive infinity to simply describe the behavior of our function. So in writing that the limit as x approaches 0 from the right is infinity, we're not saying that the limit exists. We're not saying that the limit exists, nor are we saying that there is a real number that your function values approach, because there is no real number, right? Because infinity is not a real number. This expression is just a nice way of saying that the limit does not exist because the function values are approaching positive infinity. Now, something similar happens as x approaches 0 from the left, the function values become arbitrarily large and negative, right? Large in magnitude here. So we'll say the limit as x approaches 0 from the left of our function is negative infinity. And folks, I just noticed a mistake here. So notice I'm missing the argument right here. That's a grave mistake. So please make sure you correct your notes. The limit, if I can fit it right here, the limit of f of x. Okay, make sure you change that in your notes. All right, so let's write down the equivalent statement for x values approaching 0 from the left. We're going to say the limit of f of x, let me make sure I don't forget that this time, as x approaches 0 from the left, it will be negative infinity. And everything we said earlier applies. We're not saying that the limit actually exists, nor are we implying that negative infinity is a real number. We're just describing how or why the limit does not exist. It's because the function values are tending to negative infinity. They never stop decreasing. We're going to now look at a list of just different rational functions, and we're going to evaluate some limits. And the idea for these next few rational functions is just to illustrate, just to show how rational functions can behave in a number of ways near the zeros of the denominator, all right? So we've already examined some limits earlier today in this lesson, and we're seeing how a lot of times for a rational function, there's an asymptote, whether it's a slant asymptote or a horizontal asymptote or whatever it is. I want you to consider the following functions and the limits of these functions near the zeros of the denominator. All right, so let's check out this first one. So we have the limit of x minus 2 quantity squared over x squared minus 4 as x approaches 2. Now, we cannot just substitute, right? We cannot use direct substitution because the denominator is 0 at 2. And so what we're going to do is we're going to have to manipulate or simplify this expression. And so we can do that by factoring. So the numerator is already factored. We all know that x minus 2 quantity squared means x minus 2 times x minus 2. The denominator, you'll recognize that as a difference of 2 squares. So we can factor that as such. So then this is equivalent to the limit as x approaches 2 of simply x minus 2 over x plus 2. Now, at this point, you can substitute 2 into our expression in order to evaluate the limit. Now, remember that just because a function is not defined at a particular value, call it c, does not necessarily mean the limit doesn't exist at c, right? So our function is not defined at 2. That you would find that there would be a hole in our function, right? A point of discontinuity at 2. But although that is occurring, the limit can still exist. So now we use direct substitution, and we find that the limit is, 0 over 4. Okay, the limit is simply 0. Notice that the limit near 2 is a real number. Let's look at another function. Now we have the limit of x minus 2 over x squared minus 4 as x approaches 2. Again, we cannot just we can't just use direct substitution here because the denominator is 0 at 2. So we're going to use the same strategy as before. We're going to simplify this expression using factorization. So the denominator, again, factors as x plus 2 times x minus 2. So then this is equivalent to the limit as x approaches 2 of 1 over, forgot to close that parenthesis here, make sure you close that parenthesis, 1 over x plus 2. Now the denominator is no longer 0 at 2, so we can use direct substitution. And when we do, we get the real number 1/4. Awesome. Again, another real number. Let's look at another function. Now this one's going to be interesting. The limit of x minus 3 over x squared minus 4 as x approaches 2 from the right. Now, we do know that 2 is a 0 of the denominator. All right, so let's see how this function is behaving as x values approach 2 from the right. So once again, notice that the denominator does factor, so let's go ahead and factor that. We have factored that a number of times already as x plus 2 times x minus 2. All right, so we know that as x, I want you, please lean in here, as x approaches 2 from the right, x minus 3 is approaching 2 minus 3, which is -1. So as x values get closer and closer and closer to 2 from the right, the numerator is becoming -1. Now keep that in mind. Now let's look at the denominator. As x values approach 2 from the right, let's consider what the denominator is becoming. So as x approaches 2 from the right, this factor here is approaching 4. So let me write that down. X plus 2 is approaching 2 plus 2, which is 4. That's the denominator now. Finally, as x approaches 2 from the right, now this factor here we know is approaching 0. Okay, we know it's approaching 0. But this is the point I want to make. As x values approach 2 from the right, this factor is approaching 0 through positive values. Like imagine if x is 3, then this is 3 minus 2, which is positive 1. Imagine if x is 2.5, then this 2.5 minus 2 is 1/2, positive 1/2. Imagine if x is 2.1, then this is 2.1 minus 2, which is positive 0.1. I think you understand what I'm saying. As x approaches 2 from the right, yes, this factor is going to 0, but the point of the matter is it's going to 0, it's approaching 0 through positive values. So, in conclusion, the numerator is approaching a real number, which is -1, and the denominator is getting smaller and smaller and smaller, right? This entire denominator, this factor here is approaching 4, but this factor here is getting infinitely small. So then the whole denominator is getting infinitely small through positive values. So you have a numerator that's approaching a negative value, and you have a pot, and it's going to be constant, right, at -1. And then the denominator is approaching 0 through positive values. Therefore, this ratio is negative infinity, right? Because that's a weird looking infinity. Sorry about that, but it is negative infinity. When you have a fraction and the numerator is a constant and the denominator keeps getting smaller and smaller and smaller, then the ratio is approaching infinity. Okay, in this case, it's negative infinity because the numerator is approaching a negative value while the denominator is going through positive values. I mean, just imagine, let's say this were like -1 over, let's say positive 1 over 100, right? This is pretty small down here, and it is positive. We all know that this means -100. So that's a, pretty large number in magnitude. Imagine if this is -1 over 1 over 100,000. So I think you understand what I'm saying. Now this is -100,000. So as the numerator is approaching -1 and the denominator is approaching 0 through positive values, the ratio is tending toward negative infinity. Let's look at a different function now. So this is the same function. So the only difference is that we're allowing x to approach 2 from the left. So the answer here is going to be positive infinity. Let's see if you and I can show that. All right. So let's go ahead and factor this denominator. I think it'll be more clear as to how our function is behaving near 2 if we factor. And I meant to factor. Sorry about that. So x plus 2 times x minus 2, right? We factor that difference of 2 squares a number of times. All right, cool. So let's see. Let's do this. As x values approach 2 from the left, x minus 3 is approaching 2 minus 3, which is -1. All right, so that's the same as before. Now let's look at this denominator. So as x approaches 2 from the left, this factor x plus 2 is approaching 2 plus 2, which is 4. All right, cool. As x values approach 2 from the left, now here we go, x minus 2, right? It is approaching 0. It's getting smaller and smaller and smaller. But as x values approach 2 from the left, let's imagine x is 1. 1 minus 2 is -1. Imagine if x is, I don't know, 1.9. 1.9 minus 2 is -0.1. So the idea is that, yes, it is approaching 0. This factor is here, which means the entire denominator is approaching 0. But it's approaching 0 through negative values. So you have a numerator that's approaching a negative real number, and you have a denominator that is getting increasingly small, right? Infinitely small, but through negative values. So you have a negative over a negative, right? Which shows that this ratio is going toward infinity. Now, I do want to highlight that, remember, we already saw that as if the limit of our function is approaching infinity or negative infinity, it must mean that there is a vertical asymptote at that location in the graph. So we can conclude that this function has a vertical asymptote at 2 because the limit is infinity. The same thing is true for the previous function. Actually, it was the same function, wasn't it? But x was approaching 2 from the right, and we found that the limit was negative infinity. That means that there's a vertical asymptote at 2 for this function. All right, let's look at a new function. Okay, I lied. It's the same function. All right, but now it's x approaches 2. Folks, this does not exist because we already showed that the limit of this function as x approaches 2 from the right is not the same as the limit of this function as x approaches 2 from the left. The one-sided limits differ, right? Therefore, the limit as x approaches 2 does not exist. All right, very good. All right, now for real this time, let's look at a different function. All right, this is the limit of 2 minus x over x minus 2 quantity cubed as x approaches 2. Once again, we cannot use direct substitution here because the denominator is 0 at 2. All right, so let us simplify. So this is equivalent to the limit as x approaches 2. Now, what I want you to notice is, well, you probably already noticed it, the numerator, this factor, 2 minus x, is the opposite of x minus 2. And so opposites do divide out. And when you divide out opposites, your quotient is negative 1. So because of that, we know this simplifies as negative 1 over x minus 2 now squared. X minus 2 quantity squared. Okay, folks, so we do know that the numerator is fixed at a negative value. So the numerator is negative regardless, and it is constant. It's fixed at negative 1. We also know the denominator is 0 when you plug in 2, right? But as x values get closer and closer and closer to 2 from both sides, not only is this approaching 0, the denominator, but it is doing so through positive values, and we know that because the denominator is being squared. So regardless if you let x approach 2 from the left or from the right, once you subtract 2 and then square, the result will always be positive. So you do have a denominator that's getting infinitely small, right, approaching 0, but it's doing so through positive values, while the numerator is negative. So therefore, this ratio is negative infinity. So this shows us that this function has a vertical asymptote at x equal to 2 because the limit is not a real number. All right, check out this rational function, 2x to the 5th power minus 6x to the 4th plus 1 all over 3x squared plus x minus 7. And we're asked to consider the limit of this function as x approaches negative infinity. So this is a limit at infinity. Now, what we want to do is, well, the purpose of this example is to show that this is an infinite limit at infinity. An infinite limit at infinity. The answer here is going to be negative infinity, so it's going to be an infinite limit at infinity. Okay, folks, because we're being asked to find the limit of this function as x approaches negative infinity, this is the case where we use that technique where we divide every term in the numerator and every term in the denominator by the largest variable power that appears in the denominator. And the largest variable power that shows up in the denominator is x squared. So we're going to divide every single term by x squared. Now, when we do that, when you divide 2x to the fifth power by x squared, you get 2x cubed. Minus, when you divide 6x to the fourth power by x squared, you get 6x squared. And when you divide 1 by x squared, you have positive 1 over x squared. All right, that's the numerator. Now the denominator, divide every single term by x squared. You get 3 plus 1 over x minus 7 over x squared. I just divided every single term in the denominator by x squared. Now, I think what I would like to do, I forgot to write equals earlier, so equals, one more thing here before I consider what the answer here is. The first two terms in the numerator have a common factor of 2x squared, so we can factor that out. That might help us think about this a little bit more. All right, I think that's good. Just rewriting everything else we have. All right, so now what I want us to do is I want us to consider what each of these terms are approaching as x approaches negative infinity. Let's talk about 1 over x squared. As x values approach negative infinity, this denominator becomes positive because it's being squared. When the numerator is fixed at 1 and the denominator is getting infinitely large and positive, this ratio here is approaching 0. So I'm just going to do this if you don't mind. I'm going to say this ratio is approaching 0. The same is true for this ratio down here in the denominator. It's approaching 0. And for this one here, x is getting, x is tending to negative infinity. And so this ratio here, it is approaching 0 as well, and it is doing so through negative values, but at the end of the day, it's approaching 0, which means this entire denominator approaches 3. As x approaches negative infinity, the denominator is approaching 3. Now, if I'm going to scroll up a little bit here, all right, so we got the denominator. Now let's talk about this numerator. Well, we already know that this term is approaching 0. Let's talk about, now we do know what's happening here. As x values approach negative infinity, x is getting really, really large, especially because it's being squared, and it is positive. So this factor here is getting really, really large, tending to positive infinity. And this factor here, though, remember, x values are getting smaller, tending toward negative infinity, and then minus 3. So this here is making the entire numerator approach negative infinity. So we have a numerator getting very, 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 very large in magnitude and a denominator that's fixed. So because of this, because of both of these statements here, we know that the limit here is negative infinity. Okay, so let me write that down. The limit of our function, I'm just going to call the function f, okay, is negative. Here, let me see if I can write that nicer. Okay, so negative infinity. That's nicer, right? The limit as x approaches negative infinity is negative infinity. All right, very good. This definition here for a vertical asymptote of a graph of a function really summarizes well what you and I have been finding for each of these examples. If you and I can show that the limit of a function as x approaches a from either the right or from the left is positive or negative infinity, then that shows that or defines a vertical asymptote at x equal to a. What's important here is that the limit is either positive or negative infinity. The limit is not a real number. For horizontal asymptotes, we know that the graph of a function will have a horizontal asymptote, let's say at y equal to b, where b is the ratio of the leading coefficient of the numerator to the leading coefficient of the denominator. So we know that the graph will have a horizontal asymptote if you can show that the limit at infinity, right, at either positive infinity or negative infinity, is a real number, a real number. Then that real number is or defines a horizontal asymptote for the graph. So this is a limit at infinity equal to a real number.